Hey y'all, today we are going to learn how to calculate the potential of a cell when that battery is not at our standard conditions. But first, let's talk about what we just learned in the last video, recap that, and then we'll get into the new content right away. In the last video, we talked about how changing the conditions away from standard, which remember means 1 molar concentration or 1 atmospheric pressure, is going to impact the relative voltage of the cells. In order to do this, we're going to be able to take this qualitative like we did in the last video and understand that an increase in our Q value is going to decrease our voltage, but keep it above 0. And a decrease in our Q value is going to increase the voltage. Today, we're going to actually learn quantitatively how to apply that using something called the Nernst equation. So let's take a look at this Nernst equation and see how we're going to apply it. Here's the Nernst equation. So let me just go through a quick rundown of what we're seeing here. The first thing that we're looking at is that the E of cell has two forms. One is with the degree sign, and one is without the degree sign. The E cell that we're solving for here is the non-degree sign version. This is the voltage that we're actually going to see in a battery with a non-standard situation, okay? But it also could be with a standard situation. I'm going to talk about when that circumstance is going to occur. The E with a degree sign would be assuming standard conditions, 1 molar concentration or 1 atmospheric pressure of all of our battery's components. The second term that matters here is that second half, minus RT over NF times the natural log of Q. That part is going to be a little bit more complicated, so let's take a second to look at what each of those variables means, and then we'll dig into how that can change. So here's a quick list of all of those different variables. N is the number of moles of electrons transferred. F is Faraday's constant. The R is our gas constant, but remember we're using units of energy here, so we're going to use 8.314 in this situation. And T would be temperature in Kelvin. Now, the Q value here, if you remember, is going to be predicated off of the relative ratio of our reactants and products. Because our reactants and products that we care about are only going to be the ions, concentrations, or in the case of gases, their partial pressures, we need to take that into account. So our Q value here is actually pretty simple. So in the circumstance of two ionic solutions, it's simply going to be the concentration of our product ions over the concentration of our reactant ions. So let's just do a quick example. We're going to apply the Nernst equation to a standard battery. In this case, we're looking at a copper-iron battery where we have copper 2+ and iron 2+. In this case, when we look at the E of reduction values, the copper is going to be reduced, the iron is going to be oxidized. So the E of the cell that we would predict at standard conditions is a positive 0.78. So 0.78 volts, that's our voltage of a standard battery. Now, when this is a standard battery, that means our concentrations of each of those ions, the iron ion and the copper ion, are going to be both 1 molar. If we set this up as a Q, you'll understand that it's going to be the concentration of our product, which is iron ion, over the concentration of our copper ion, both of which equal 1. So when we put this into our Nernst equation, E of cell is equal to E naught of cell, or E with a degree sign of cell, minus RT over NF, natural log of Q. Q in this case is equal to 1. Because the concentrations of copper and iron are both 1, it is equal to 1. Therefore, the natural log of 1 is 0, and that entire term, RT over NF times the natural log of 1, is all equal to 0. Thus, at standard conditions, E of cell is equal to E with a degree sign of cell, or E naught of cell. So what happens to the voltage if we start changing things around? We're going to make it into a non-standard cell now. In this case, we're going to increase the concentration of our iron ion to 4 molar, and we're going to increase the concentration of our copper ion to 2 molar. In this circumstance, our Q value is now going to equal 2. When we plug this value in, now all of a sudden that term, RT over NF times the natural log of Q, is no longer equal to 0. Instead, it's equal to RT over NF times the natural log of 2. When we plug this in and we solve, what we find is that the voltage of our cell, the E cell, is going to equal 0.78 minus 0.01. That gives us a new E of cell the voltage that we're actually going to see, the one without the degree sign, of 0.77. Now you'll see that this is a very small change from our standard battery, but at the same time, it is a change. We have a reduced voltage compared to what we had at standard conditions. Now, if we think back to our last video where we talked about this qualitatively, you'll remember that we just increased the concentration of our product ion more than we increased the concentration of our reactant ion. Therefore, we caused our Q value to increase. When we caused our Q value to increase above 1, that caused our overall voltage to decrease as a result. So let's look at the same cell, but instead we're going to make another change. In this case, iron ions, the concentration has been kept at 1 molar. The copper ions are now at 2 molar concentration. I want you to take a second, and using the Nernst equation, I do want you to try to solve for the actual voltage that you would see as a result of these changes to the half cells. Take a second, pause the video, solve for the voltage, and then when you're done, come back and we'll talk about it. So, did you get a voltage of 0.79? If you did, you're right. Let's talk about why. When you take the new Q value, which goes from 1 in a standard cell to, in this case, 1/2 in this non-standard cell, when we plug it in, we find that the voltage change as a result of the non-standard conditions is only 0.01, and it makes it positive because, remember, we're subtracting a negative number, right? Subtracting a negative number in this case makes it more positive. So the voltage of our cell, of our battery, goes up by 0.01 in this case. So our new voltage is 0.79. In the practice problems we just did, the iron and the copper were at a 1-to-1 ratio. Because of that, let's say we doubled both of their concentrations. In the end, that wouldn't affect the Q value at all. So if we made their concentrations 2 and 2, the Q value actually wouldn't change away from 1. But that's the thing. The ratio might not always be 1-to-1. Maybe we're in a situation where the ratio is 1-to-2 or 2-to-3. In that circumstance, changing the concentrations away from standard conditions would affect all of our Q value calculations because of the fact that we'd be maybe squaring one and cubing the other, right? And as a result, that would affect the overall Q value. So be careful. Whenever we're doing this qualitatively and thinking about this, you need to understand that the Q value isn't always going to need to be calculated. But at the same time, it sometimes helps to calculate the Q value to make sure you know exactly what's going to be happening to the overall voltage of the cell. So in the end, the Nernst equation is going to be on your formula sheet, and it is going to be very helpful for providing a piece of supporting evidence to explain relative changes in voltage. However, you will never be asked to calculate the new voltage of a battery using the Nernst equation. You can use it as supporting evidence. You should use it as supporting evidence. But again, you're never going to be doing the calculations themselves. If you ever need to use this, just be careful to make sure that all of your units are in the right format and you're using the correct gas constant, because in the end, those are the most common mistakes that are made. Also, when you're calculating your Q values, make sure you're using the coefficients to create the exponents, because that is also a common mistake that can be made when applying the Nernst equation. When you are in a situation on a test, though, 9 out of 10 times you're going to be using the Nernst equation to discuss something that is qualitative, not quantitative. So that wraps up today's video. Let's do a quick recap. Today we learned how to use the Nernst equation both qualitatively and quantitatively. Remember that when you are using the Nernst equation, if your Q value is less than 1, your voltage is going to be greater than that at standard conditions. If your Q value is greater than 1, then your voltage is going to be less than that at standard conditions, but still greater than 0. When you're using the Nernst equation, you never have to actually calculate the voltage of the cell, but you can use the Nernst equation as your supporting evidence to be able to describe what the relative voltage change would be. The other thing to keep in mind is that with the Nernst equation, calculating the Q value can be really helpful because you'll have to remember when there's a non-1-to-1 ratio between the ions, it won't necessarily impact the Q value the way that it would if it was a 1-to-1 ratio between the ions. So keep in mind that sometimes calculating the Q value itself matters, but you'll just never necessarily have to then put it back into the Nernst equation to then solve for the E of cell. Today's video was written, filmed, and edited by Rayan Padaria and Jacob Kaplan. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.